So we're going to continue the theme of the deformation to the normal cone, but in a slightly different context. There will be K-theory, at least eventually. There will be K-theory, but there won't be Dirac operators. So, I don't know. That's what we're doing. I realized I have enough stuff here for 2 lectures, so we'll see how far we get. Okay. Suppose you have a Lie group. Then it has a Lie algebra, of course. Or anyway, it has Lie algebra. And this function made an appearance in the notes. I think actually in the notes, not just in the exercises. It's the determinant of conjugation by the element little g on the Lie algebra of G, like that. This is by the properties of the determinant, this is a group homomorphism from the group to the group of positive reals. And the reason I'm mentioning it now is I want to talk about convolution algebras. And there is this funny tension between what convolution algebras are in the world of groupoids and what they are in the world of harmonic analysis. And this fellow resolves the tension, if that's the right way of putting it. Okay, so temporarily, let me put the word right up here. If you take the smooth compactly supported functions on G, you can make this into a star algebra by convolution, exactly as we were doing. So this, I added the word right because we were using right Haar systems when we built this thing. And so this is what we were speaking of, for example, in a more glamorous context when we were building the C-star algebra of the tangent groupoid, except now we're talking about groups, not groupoid. And we have a version of this, a sort of left-handed version, which is more common in realms where people study representations, Fourier transforms, and so on. It's called harmonic analysis. And both of these vector spaces are the same vector space of smooth compactly supported functions. But in the left-hand one, we use the left version. I'm only going to write this decoration left for a little while, and then I'll get tired of it, and it'll disappear. And that's what you get from the right Haar version just by sticking in, as it happens, this factor here. So the integral on the right is the one that we were talking about in groupoid theory, and the integral on the left is defined, if you like, in terms of the integral on the right in this way. And this makes a left translation invariant integral. You can check. It's in the notes. I did check. Okay. And when you do that, the appropriate way of multiplying functions is like this. Oops. And for our purposes, the appropriate way of taking an adjoint is this. You don't have to put this in to get a legitimate adjoint, but this is the good one for harmonic analysts for a reason that you'll see in a moment, like that. So that's a star algebra. And it's not a new object, it's equal to the old object. So here's I can't remember which way around I did it. I'll do it right, because although I just did it before class, I can't remember. Yeah, we put the right one on the right. No, that's the left, but anyway, here's where it's going to go. We have a function here. So this is the world that we've become accustomed to. And here's the world that we're going to be talking about. Yes, I should have put the left on the left and right on the right. There you go. This here is just pointwise product, not convolution. And the reason that people want to make these funny definitions is the following. That if you have a unitary representation of the group, then you can make out of it a representation of the left algebra. This each. In a sort of natural way. Integrate the representation, as they say. What does this integral mean? This is some integral of the smooth function with values in some topological vector space with a weird topology. It's easy to make sense of this integral. This object is the unique object, so that when you take its inner product, you apply it to a vector, and then you take its inner product with another vector, you can do that on the inside. So the inner product of this operator, excuse me, like this. If I put a vector here and another vector here, I can just do it like this. Maybe I should do it upstairs. Like this. So pi of f is an operator, but if I apply it to the vector v, and then take an inner product with w, I get a number. And what is that number? It's the number you get by integrating f of g against this scalar function. So now it all makes sense. Of course, that begs the question of whether or not the operator exists. This integral exists, and it does. That's a little exercise. Yeah, so replace this fellow by this fellow. How about this? I guess make and replace this fellow by this fellow. Then you have a number equals an integral of numbers. So we know what that means. And that's what we're talking about here. However, having said that, we're not going to dwell on such details. Then this thing here is star representation. If you use the the right version of everything, you could survive, you could get by, obviously, because the left and the right versions are isomorphic. But it would look a little funny, wouldn't it, with all of those square roots of modular functions in it? So it's a little messy with these things. I'm just going to get rid of them for posterity. There. No. this is related to some things in representation theory. For example, how you define characters in representation theory. But yeah, but this is nothing fancy. I would not put, I don't think Langlands would want to put this and his name on the same piece of paper. All right, and now you can do the following thing. Build a C-star algebra norm by just taking the sup over all representations pi of f. So that thing's a bounded operator on whatever the Hilbert space is. And then you can complete and you'll get the C-star algebra of G. And there's something called the reduced C-star algebra, where you just take the norm of lambda of f and b of 2 of G. And lambda is just the regular representation. This L2, maybe I should say, is the L2, the way I've written it here. You build with the left integral, the one here. So we get a couple of C-star algebras, the so-called full and reduced group C-star algebras. And the little one, well, may not be clear which is the little one. The reduced one is the same as the fellow we were previously studying via this isomorphism here. I guess I should make it match up the other way around via this isomorphism star. And now we have a new friend, the max one. And annoyingly, for everyone, they're not the same. But there you go, all the time. Is that a question, or you just, yeah?
Is it possible to get the representation of the star algebra of G that doesn't come from representation of G?
No, I'm going to say that next. Yeah, that's not. Just CC infinity of G. And just an algebra representation. Yeah, then it is possible. Yeah, you can do some weird things. But maybe not a star representation. Certainly a representation which wasn't a star representation. Probably you can get a star representation too. CC infinity of G wants to be equipped with some sort of, I don't know, topology. And when you put a topology on it, then you have a much better chance of saying you'll only get representations from unitary representations. But I'm not going to commit myself to just CC infinity of G by itself. All right. Yeah, once it's L1 continuous, you're committed. Then you're dealing with unitary representations of G. Okay. Probably for compact groups they're the same. Yeah. I'm. So I didn't mean to. I didn't mean to say, "Oh, shut up." Yeah. Okay. So this reduced fellow, if you like, is a quotient of the max one. The so doesn't go with the remark, it goes just with the definitions. Yeah. because the regular representation is just one of the representations over which you're taking the soup up here. So there's an obvious continuous map from C star max, C star that is, to C star reduced. And the image of a C star algebra homomorphism is always closed. And that means it must, in this situation, be surjective.
Okay, that's the big one where you take the super off.
Yeah. Yeah, I'll get to that in just a moment. Yeah, the answer is yes. Yeah, let's put these issues to rest by talking about the spectrum of a C star algebra. So this thing is written with a hat like this, and this is just a set of irreducible the zero representation on the zero Hilbert space is never allowed. People don't want to think of that as an irreducible representation. Irreducible representations of A as bounded operate star representations of A as bounded star representations on Hilbert spaces, up to the obvious notion of unitary equivalence. I'll put in unitary. And this process of integration this process here is reversible in the sense that it's an equivalence, actually an isomorphism from the category of unitary representations of G. When you talk about unitary representations, there's just a little bit of continuity which is built into the definition of what a unitary representation is, which I'm not mentioning. You can figure it out on the basis of this theorem. This category is equivalent, in fact, isomorphic to this category here, consisting of non-degenerate representations of C star G. And this word non-degenerate in general means that there's no part of the Hilbert space on which A acts just as zero operators like that. So the spectrum of C star of G is the same as the unitary dual of G, the set of irreducible unitary representations of G up to unitary equivalence, which is something that people want to know about. Inquiring minds want to know for various groups what is the unitary dual of G, and you might ask, is it of any value to convert that question into a question about C star algebras? You can. The question is there any value in doing that? Well, one thing you can do is right away is equip the unitary dual with a topology using this C star algebra perspective, and we're going to be doing that throughout. In fact, I would say that if you're going to invest in C star algebra technology in representation theory, you ought to be doing it for this reason, that C star algebras give a particularly transparent way of thinking of this guy as a space, as a topological space, like this. This is called the whole kernel Jacobson or Fell topology. And we can do it in this context here for any C star algebra at all.
Sir, I had a question.
Yeah.
So when we are discussing spectrum of a C star algebra, so we know what is the spectrum of a linear operator or something like that? So spectrum of a linear operator. So how do you, is there any relation between spectrum of an algebra and a linear
Yeah,
operator?
That's a good point. I suppose I should have given an example. We'll come back to groups, whole kernel and so on in a moment. But as an example of this spectrum business, the spectrum of the C-star algebra of continuous functions on a compact set, how do you get a representation of C of x? Well, you could evaluate a function at a point, and that would be a number, which is a 1-by-1 matrix. In other words, an operator on a one-dimensional space. So each point gives an irreducible representation, and that's the only ones that you get, which are irreducible. And as for your question about operators, suppose you have an operator on a Hilbert space, and suppose it was, well, for example, self-adjoint. Then the C-star algebra of T has a spectrum. Actually, the C-star algebra of T is a commutative C-star algebra, and it's isomorphic to continuous functions on the spectrum. So in particular, the C-star algebra, the spectrum of the C-star algebra of T is the spectrum of T. So there is some connection between these things.
Thank you.
Sorry, I'm digging deep in my background. That's sort of like the basic functional calculus.
Yeah. Yeah. Yeah, you start off with an operator, you want to know what can I do with it. Maybe you want to take the square root of the operator. Well, if you know that the C-star algebra generated by T is just continuous functions on the spectrum of T, you could try to somehow define a square root by taking a pointwise square root of whatever function T corresponds to on the right-hand side, which you can do sometimes. I guess you can always do it, but you can do it naturally sometimes. Anyway, this whole kernel topology has, I don't know, or open or closed. Let's talk about the closed sets. So there's one closed set for each ideal, closed two-sided ideal. In A, and the condition which builds a closed set out of an ideal is just this. So 1 for each closed two-sided ideal. It's sort of like the Zariski topology that you learn about in algebraic geometry, which is well known to be a dreadful topology. But here it's a nice topology. If you do this, if you build a bunch of open sets, closed sets, their complements are open, in the spectrum in this way, and you apply to those examples which are at the top, you get the topology on X that you started with. That's because C-star algebras have lots and lots of ideals, not all of them, but something like C of X has lots and lots of ideals. So that's what we'll be talking about. We make a topological space out of the spectrum in this way. On the face of it, if you come from algebraic geometry, you think, oh, it's a dreadful topology. But actually, in examples which are not too far removed from the commutative, it's a very good topology. Yes?
Sorry, if I'm understanding it right. The whole kernel topology is for each closed two-sided ideal in A, you look at the representation for which J is in the current.
Yep. Yep. And so it's a fact that this collection of closed sets satisfies the axioms for a collection of closed sets in a topology. It's also a fact that you can extract J from F sub J, so that different ideals always give you different closed sets. There's a bijection from closed sets to ideals, ideals to closed sets, given by this formula. None of those things is completely trivial, but they're all true.
It's sort of like how you that somehow like that corresponds.
Yep. Yep. Each closed set gives an ideal, namely all the functions which vanish on that closed set. And those are the only ideals in C of X. and by the something or other, one of these theorems, Eurozone, T2 extension or something, once you know the ideal, you know the closed set and vice versa. Broadly speaking, we want to understand the topological space, which is the unitary dual, together with this topology, except that that's a really difficult question. So we'll be interested in an easier question, which is trying to understand something about this. This is, I guess maybe I should call it R for reduced. The spectrum of C star. I guess we weren't writing it like that. We were writing it like this. So C star reduced of G is an ideal, excuse me, a quotient of C star of G. So it corresponds to an ideal, the kernel of the regular representation. And according to the definitions above, this thing here is a closed subset of the whole unitary dual. You'd like to know what is the unitary dual. I mean, that's the obvious natural thing to study, but it turns out to be a very difficult thing to study. And the reduced dual turns out to be much more within reach. Back in the 1950s, Harishchandra decided that he was just going to study this thing as a set or as a measurable space. And he made an excellent choice because it took him 25 years, but he did it. He figured out what this thing is for groups like SLNR, bashed away again and again and again, and he figured it out as a measure space. What is this thing's G hat sub R? Whereas G hat itself struggles to be understood even to this day. There are computer programs which know what's going on, but not AI programs, actual serious computer programs, but it's hard for human beings to grapple what is G hat with what is G hat. So we'll study this thing. Let's not write it as a definition. Yeah, I mean, there are many ways of describing this topology, only one of which I've shown you. And some of the other ways of describing the topology lead to a much more concrete understanding of what is, apparently more concrete understanding of what is G hat sub R. For groups like SLNR that were Harishchandra's favorite friends, you can say even more what these representations are that lie in G hat sub R. Yeah, you can say a great deal, but I won't, at least not right now. You might ask, when are these two C star, I haven't finished the theorem yet. You might ask, when are these two C star algebras the same? And there's an entire subject here, and there are about 50, how many, what's it say on the Heinz ketchup bottle? 57, 47? Anyway, there are lots of different equivalent ways of saying it. But one of them that's quite easy to check is the following thing, that the trivial representation. It's the trivial representation of G, which is, of course, an irreducible representation of G, and therefore it's in this big space. If it manages to get into the reduced dual, then it brings with it, it sucks with it, all of the rest of G hat, and the two C star algebras are the same. And there's a whole bunch of others, depending on what the group is. Some are easier to check than others, but when this happens, G is called amenable. And we'll encounter, and it'll be kind of important, some examples compact groups are amenable. Abelian groups are amenable. In both cases, it's not hard to check this condition. You might want to take a class in C-star algebras before you try to do it, but it's not that hard. And you could imagine the following group. Suppose you have a compact group which acts by automorphisms on an abelian group. And you form the semi-direct product. That's also an example of amenable group. There are much more general statements to make. I only write this down, compact semi-direct product abelian, because that's what we're going to see in a little while in an explicit example. Okay, so for these groups, C star max is equal to C star G. C star max is another way of, let me say that again. For these groups, C star max is equal to C star reduced. That's what I wanted to say. And then I wanted to say, as a remark, that when people say C star max of G, they just mean C star of G. Sometimes you just can't help saying the max. Okay, it's the one at the top, the biggest. Every other C star algebra of G is a quotient. Okay, there's a flip side to this. Where's my eraser? Here it is. It's a definition, and then the theorem is that there are examples. G is a group G, one of our Lie groups, is said to have property T. If there is a projection in C star of G, the max C star algebra, so it's self-adjoint, and it's idempotent. That's what a projection is. With the property that in any unitary representation, which I can think either as a unitary representation of G or a unitary representation of C star of G. I mean any non-degenerate unitary representation. Just to put that in. Of course, you can apply that representation to P, and now you get an operator on the Hilbert space, and that operator is a projection because pi is a representation. Pi of P squared is P. And what this thing is the orthogonal projection onto the pi of G, fixed vectors in H. Not difficult to come up with property T groups. For example, if G is compact, yeah, this function does the job. So that's an element, constant function, an element of CC infinity of G. You can forget about C because G is compact. It's like an averaging function. Remember how we integrate representations according to that integral. It's obvious from the way we define pi of P that this is the projections onto the G fixed vectors. So for a compact group, the group has property T. But if the group is not, and conversely, this is it. There's only one possible function you can write down which has the right property. There's only this projection P is a unique guy which has this property that's easy to see. And if the group is not compact, it's going to be a little difficult to make this construction because the volume is infinite. On the other hand, the group is infinite. So you'll be dealing with a function which is constantly equal to 1 over infinity, but over an infinite amount of space. So, I mean, the good news is that the integral should just be 1, right? Because you're integrating 1 over the volume over the volume, so that should just give you one. On the other hand, what exactly this thing is actually supposed to be is a bit of a mystery. And so it's a bit of a remarkable theorem that, for example, this is the first one that everyone discusses. This group here has property T. Theorem of both a definition and a theorem of Kashdan. T for trivial, I guess. Yeah. The legend is that Kashdan was going to the International Congress and was thinking to myself, damn it. And just like you have these nightmares, right? In the nightmare, you're going to a conference and you don't have anything to say. You didn't prepare a talk and you didn't manage to prove anything. You don't have anything to say. So this actually happened to Kashdan on the train. So he had nothing to say. What am I going to talk about? So he just invented this on the train. And now careers are spent examining the consequences of Kashdan's nightmarish train trip. So there you go. It's a beautiful, beautiful subject. There's a beautiful book two beautiful books by Alain Villette and co-authors, which examine this subject. I really recommend it. If you have a group which has property T, it's very easy to see that it breaks up in a kind of an interesting way as multiples of this projection P direct sum the kernel of the trivial representation, the augmentation ideal, if you like, of G. It's the direct sum of two mutually annihilating ideals. If you take the product of something on the left with something on the right, you get zero. So that's what the C-star algebra is. There's a bit which is just like the complex numbers, and a bit which is like the kernel of the trivial representation, whatever that is. And this is a sobering lesson. If you look at this map in K-theory, which is associated to the projection from C star of G to this quotient, the reduced C star algebra of G, what's going to happen to this projection? What's going to happen to this summand under the C star algebra map from C star of G to C star reduced of G? Well, that's C star reduced of G is built using the representation, which is the regular representation, this guy right here. And if the group is not compact, then this has no G-fixed vectors. The G-fixed vector would have to be a constant function. So P has to go to zero, according to its characteristic property in the regular representation. This fellow has to just disappear. On the other hand, the K-theory of a direct sum of C-star algebras is the direct sum of K-theories, and the K-theory of the complex numbers is Z. So there's a summand of Z in the K-theory of C-star of G, which just goes to zero over here. So this map here is not injective, fails to be an isomorphism. So what you do with these C-star algebra completions matters even at the level of K-theory. So all of this functional analysis stuff, how do you make a C-star algebra out of a group? Well, exactly how you do it matters even at the level of K-theory. So that's a little bit sobering. It means if you're mucking around with K-theory of C-star algebras of groups, then it's not just about topology, it's about harmonic analysis in some complicated way, right? It matters whether or not the group has property T. And that's a complicated thing to resolve, whether the group has T or not. All right. That's all I want to say about property T. That's a cautionary note about K-theory. That's all I wanted to say about it. Okay, now, the main topic of today is the following. So we'll see how amenability is going to rescue us at a certain small point in the following discussion. So we shall use amenability in just a moment. We won't use property T. This is just a cautionary tale. Don't want you running off and getting into trouble trying to calculate the K-theory of C star of G. Just don't do that. Unless the group is compact, then you're in this situation. Then it's okay. You can attempt to calculate the K-theory of this, no problem. Just don't attempt to calculate the K-theory of this, except when these two guys are equal. Second? Oh, yeah, sure. Yeah, that's a very good question. SL2R is also not amenable. And it's interesting that when you attempt to prove this theorem, there's a strange sort of bootstrapping which is involved. The typical way that you prove that SL3R does have property T is by first observing that SL2R is not amenable. It plays a role in the proof that SL3R has property T. Yeah. Maybe I'll just, since you asked, let's stick in another equivalence here, I guess. And the other equivalence is like this. There's a collection of vectors in L2 of G, unit vectors, such that these functions, Fn, lambda G, Fn, so that's a function of G. This should converge uniformly to 1 on compact sets. Well, these functions of G should converge to the constant function uniformly on compact sets. That's easy to arrange, for example, on the group G equals R, easy to arrange on a compact group. I mean, you can just choose Fn to be 1, the normalized version of the constant function 1, and you're just done. And it's not possible to arrange on SL2R. What happens in SL2R is that there's a very clever argument due to Harish-Chandra, Carl Hertz, many people, which says that all of these functions have the same, this is roughly speaking true, they have the same rate of exponential decay. These functions, what I'm saying is slightly not true, but I'll say it anyway. These functions have a uniform rate of exponential decay, so they couldn't possibly converge to the constant function 1. In the sense that if a group had, for example, polynomial growth, it would be easy to check that these two things are the same. It would be easy to verify this condition using so-called Follner sets. In fact, if the group has sub-exponential growth, it's not so easy, but still true that it must necessarily satisfy this new condition I wrote down. All right, good. Yeah.
Okay, when the group is compact,
Yeah.
both handles and
Yeah.
Okay, then it's not adding up to me. So these two derivatives are the same, and the K theory is not exactly.
Oh, so thank you very much. If the group is compact, then this projection doesn't go to 0 over here. Yeah, it doesn't go anywhere. It stays exactly where it is. Yeah, the fact that the projection went to 0 was based on the fact that there were no G-fixed vectors in L2 of G, and that's true when G is not compact. All right, good. Now, so for this lecture and the next lecture, and at the rate I'm going, the lecture after that, we'll talk about these groups. Connected, real, reductive, Lie group. So these have various definitions, but the bottom, oh, I missed off a word here. Let's make them all, as they say, linear, because that simplifies the story a lot. Connected linear, real reductive Lie group is a closed connected subgroup. This is what linear is all about. Sitting inside of some G, L, and C, like that. Doesn't matter what this is. With the property, just one more property apart from those, that the group is adjoint closed. It's, as they say, symmetric. For example, all of GLNC. Not all of GLNR, because it's not connected, but all of SLNR is connected, so that satisfies all of the requirements. All of these groups, SOPQ, that you learn about in physics, they're in the collection. The symplectic groups that you learn about from Eckhart, those are in the collection and so on. These groups are the ones we're going to be talking about. And it happens that these are all unimodular. So you may say to yourself, well, why was he rabbiting on about the modular function? Well, these are all unimodular. So I didn't have to. There you go. Unimodular, yeah, thank you very much. We mentioned the function delta, the so-called modular function at the very beginning. I mentioned it. Unimodular means that that function is identically one. So in that case, there is no difference between the C-star algebra from the world of groupoid and the C-star algebras from the world of harmonic analysis. So all of that talk was for nothing, but I felt that I needed to tell you the truth about what was really going on. Yes, it means that, yeah. So we'll be studying these groups, like, for example, SLNR, and it won't do you any harm at all to keep in mind only two examples, SLNR and at some point, probably in the next lecture, SL2R even, and also SL2C. If you have those two examples of groups of 2x2 matrices in mind, you're going to be in good shape. Okay. People hate definitions like this because it's not intrinsic, you know. Well, it's not, it's hard to give an extrinsic definition. I mean, an intrinsic definition. This is an extrinsic definition. It's hard to give one, and the ones that you can give they're not altogether satisfactory. You always have to add a little something, a little footnote. But these are the groups. This is a slight simplification of the class of groups that Harishchandra studied in his famous work. But this is basically what Harishchandra studied, and it's what we're going to study. Let me not say more about it. If you have such a group, you can look, I don't even have to write it like that. Here's an obvious subgroup. It's just G intersected with the unitary matrices. And as for the Lie algebra, this Lie algebra consists of two parts. The first part is just, it turns out, the Lie algebra of K. It's the set of all elements of the Lie algebra which are skew symmetric, like that, rather skew adjoint. And then there's all elements in the Lie algebra which are self-adjoint. And this is a vector space decomposition because G is closed under the adjoint, G the group, and therefore G the Lie algebra is 2. So you can always break up the space into imaginary and, so to speak, imaginary and real parts like this. This fellow is always a connected group, and of course compact. And there's a beautiful picture of what G the group looks like based on what you see here. G the group. It's just the product of K times all of the things you get by exponentiating things in P, like that. And in this way, the group is diffeomorphic to K times P. Not isomorphic as a group, but diffeomorphic. So these groups are quite easy to understand as topological spaces, as K spaces for that matter. Yeah, K plays, in short, a prominent role in understanding these groups. No question? No. Yeah. Yeah. If you take the group of non-zero complex numbers, that's an example of one of these real reductive groups. That's GL1, C. And the K in that situation is a unit circle, and the P, or the exponential of P, is a ray inside of the non-zero complex numbers. And so we're doing polar decomposition here. And this is called the Cartan decomposition. And the so-called Cartan motion group. I'll always write it with a 0 like that. It's just one of these semi-direct products that we talked about before. When I write P here, I mean just the abelian, if you like, vector group P. Just the real vector space P thought of as a Lie group. K acts on P by conjugation, by the adjoint action, and so you can form the semi-direct product group like you do in algebra, and that's what G0 is. And as a space, it's a Lie group, and as a manifold, it's just K times P, like G is. So there's a certain resemblance between G0 and G. They're, for example, diffeomorphic. They're not isomorphic as Lie groups because to identify this space with the space up there, you need to throw in the exponential map, which of course is doesn't satisfy x of a plus b is x of a times x of b anymore outside of abelian situations. Okay, so there we go. So this group is not the same as G, but it's kind of similar. For example, you can think of this as the normal bundle for K inside of G. So it's like it's a group, and a normal bundle is just a vector bundle, but G0 is a group, and it's like a first order approximation to G in a very small infinitesimal neighborhood of K. And what we want to study definitely, yeah. This is when you make a semi-direct product, the thing that's getting acted on is a normal subgroup, and you can always divide out by it, and the quotient is going to be K. And that quotient group homomorphism is the vector bundle projection. Well, you'll see. I think the answer to your question is yes. Mm-hmm. This group is quite easy to understand. this is an example of an amenable group by what I said earlier. Here we go. By good fortune, I didn't erase it yet. This is an amenable group, so I don't really have to write R here because C star G and C star RG are the same. But here's the regular representation. But that's not what I wanted to study. Let me, yeah, sorry for writing that down. I will stick with my apologies. So the group G0 acts in the sense of manifold actions on the vector space V, because if you have a pair consisting of a K and an X, like we were talking about there, you can form this thing, add K of X, and you have an element Y in P. You can form add K of X plus Y. So the P part is just acting by translations, nothing fancy, and the K part is acting by the usual adjoint action, rotations, if you like, on the vector space P. And so the group G0 is acting by rigid motions, if you like, rotations and translations on the vector space P. The vector space P is the same thing as the tangent space at the identity inside of G mod K. And so this translation action is like a first order approximation of the action of G on G mod K by translation. So if you linearize that action in a certain sense, you get this G0 action on P. That's why it's called the Cartan motion group. It's acting by rigid motions on P. And so there's associated to that a representation. Let's did it again on P. What should we call this? Gamma for Cartan, AB, gamma. On the other hand, P is a vector space, so there's a Fourier isomorphism from P, functions on P to functions on P star, which is a unitary isomorphism by Plancherel's theorem. And conjugating by that isomorphism, we get another representation. Maybe we'll call that gamma hat. And the reason I'm mentioning it is that this idea that G0 is represented not just by translations on P, but also by, after you convert translations under Fourier, they become pointwise multiplications, also by pointwise multiplications on P star, gives rise to the following theorem. Here's a complete description of what this C-star algebra looks like. If I can get it right, here we go. So there's a Fourier transform operation which converts C star of P, if you like, C star of the abelian group P to C0 of P star. And if you fit that into this context, what you get is a picture of the C-star algebra, which looks like this. I'm only mentioning this because it makes the C-star algebra look, this is G0, excuse me, makes the C-star algebra of G0 very easy to understand. For example, suppose you want to know what are the irreducible representations of G0, the irreducible unitary representations. Well, they're going to be irreducible unitary representations of this thing. How can you get such an irreducible unitary representation? Well, you can just evaluate at a point in the space P0, and then you'll get, you'll get a map from C star of G0 to the compact operators on L2 of K. That's a representation. It's not irreducible because that map will be intertwined by the isotropy group of the point in P star that you evaluated at. And so you have to do a little more monkeying to get an irreducible representation. If you have any representation of any C-star algebra with values in the compact operators, it's always a direct sum of irreducible representations. And now you just have to pick out and appropriately label what the irreducible representations are. It's not our job to be representation theorists in this class. So let me just tell you what the result of that is. It's just the following description. The irreducible representations all come by evaluating at a point in P star and choosing a representation not of K, but of the isotropy group of that point. And you can imagine just from this description that this would be relevant. That's it. And on this entire collection of data, K acts by conjugation, and it's the K equivalence classes of data which do the job. What I'm trying to say is that from the point of view of representation theory, this group G0 is very, very easy. You can just write down what the representations are because you can just write down what the C-star algebra is, and that follows from the elementary theory of the Fourier transform. So it's G0 good, right? Two legs good, easy to understand, G bad, right? So that's what I'm trying to say. Okay. I guess this deserves a new board. Let's pursue this normal bundle idea. So here's a groupoid, big G. And what it is the normal bundle for the deformation to the normal cone, excuse me, for the inclusion of G into K. So as we know, that's a smooth, did I say G into K? Yeah, sorry, that was a typo. K into G, yes, of course. So I don't know how consistent I've been with this notation, but anyway, there it is. Yeah, so as we know, this is a union of fibers. And by the functoriality of the deformation to the normal cone construction, each of these fibers is in fact a group. That's not surprising because we happen to know what the fibers are. There's the group G0, which is the special fiber, which is the normal bundle, which is indeed a group. And then we know that all of the other fibers are just the big manifold, the ambient manifold. So it's just a bunch of copies of groups that we might call GT. And all of these guys are identically equal to G. So this is a Lie groupoid, or if you like, a smooth family, special type of Lie groupoid, of Lie groups. Parameterized by R. So the total space is a smooth manifold. The map to the parameter space R is the submersion. And if you take the fiber product of big G with itself over R, then there's a multiplication map from that fiber product just into BG, a pointwise multiplication map, which is smooth And the inverse map is smooth, and I don't know what else. The identities glue together smoothly, I guess. All right. Oh, I'm reading this and I'm thinking, what's that got to do with anything? Should be reading that. So here's a thing. It's now legitimately part of this class because it's tangent groupoid-ish. Certainly it's a groupoid, and it's a deformation to the normal cone. And so I think it's within our rights in this class to study this thing. Nobody can stop us. So let's do it. Here's one of these annoying theorems that we've seen from time to time, and I'm sure you didn't like any of them that occurred before. This one is, because we made some preparations now, is a little more manageable. Let's suppose we take the C-star algebras of the GTs. The reduced C-star algebras. This thing is a smooth, not a smooth, a continuous field of C-star algebras. Whenever you give a bunch of C-star algebras and you say that they're a continuous field, you have to say what are the continuous sections. And so the continuous, just like we did when we talked about the tangent groupoid, the continuous sections are generated by the smooth compactly supported functions on big G. If you have a smooth compactly supported function on big G, you can restrict it to a smooth compactly supported function on each of the GTs, in other words, an element of C star of reduced of GT for each T. And by fiat, those are continuous sections. You're not allowed to just declare them to be continuous sections. You have to check that the norm varies continuously, and that's why this lemma is a lemma, not just a definition. Yeah.
So in general, you could start with the I always want to get one of these things.
Yeah.
Is that always or
If it's compact subgroup, yeah, that's still going to work. If it's not compact subgroup, then it's complicated, and it's not always true. So there are two things to prove, one of which is very, very easy. Suppose you have one of these f's, which is in CC infinity of big G, and you restrict it to each t to get an f sub t. You'd like the norm to be continuous, and that involves proving two things, of which one is this. Obviously, the field is continuous away from zero because it's constant away from zero, but at zero, it's a little bit more complicated. And so you need to show one inequality like this and another inequality involving a limb sup going in the other direction, and you'll be done. This guy here is, so to speak, geometric. If F0 is big, that means F0 gives a big convolution operator on the group G0. And so that means there's a function on G0 such that the convolution of that function with F0 is big. And you might as well assume that function by epsilon over 2 argument is itself a smooth compactly supported function on G0. Well, if that's a smooth compactly supported function on G0, you can always extend it to a smooth and compactly supported function on big G. And now you can ask yourself, how big is Ft applied to the function that you've just built restricted to t? And the answer is that quantity, the norm of Ft applied to the function, I don't know, xi t, is a continuous function on T. How do I know it's a continuous function on T? I know it because I'm talking about L2 norms, and there's an explicit formula for what an L2 norm is. It's just an integral. And I'm just asking that the integral varies continuously with T. And indeed it does. In fact, it varies smoothly with T, and you can differentiate under the integral sign and so on. So this is easy. If this guy is big, then these guys have to be big, at least if T is close to 0, where you're doing this little extension. And it's the other inequality that's much harder. So the other inequality would be like this. I'm running out of room. In order to, we're going to make a construction in which we use not the reduced C-star algebra of G0, but to calculate this norm here, but I guess I did say, yeah, these are the norms in the reduced C-star algebra, so I shall use the norm in the max C-star algebra. That won't matter because we're dealing with an amenable group here, so the max norm is equal to the reduced norm. Okay. I'm trying to show that this lim sup is bounded above by the norm of F0. If I can show that the lim sup is bounded above by the norm of pi of F0 for some unitary representation pi, I'll be in business because the norm of F0 in the max norm is even bigger than the norm of pi of F0. Okay. And here's how you do it. Let's take the C-star algebra of the groupoid G. So that groupoid G consists, well, we know what it is. It's exactly this thing up here. Okay, so it's made out of smooth compactly supported functions on all of G. And the way I'm going to, I haven't finished this construction yet. The way I'm going to build this map is I'm going to take a function on G0, and I'm going to extend it, just like I said a moment ago, to a smooth compactly supported function on G0. And then I'll get some sort of linear map, or some sort of map from CC infinity of G0 into CC infinity of G. But it's not unique, of course, because there are many ways of making the extension. So we should divide by the ideal generated by the functions f such that f restricted to t is equal to 0 is 0. Now the map is well defined. And it gives it's a morphism into a C-star algebra. It comes from a unitary, and this C-star algebra, it's just some ridiculous C-star algebra, but I can certainly represent it on a Hilbert space. And if I have this quotient C-star algebra represented in a Hilbert space, and in particular, and I have a map from, then on that Hilbert space, I can build not just a representation of CC infinity of G0, I can actually build a representation of the group G0 in a similar way. Okay, and once I have a representation of the group G0, it becomes a representation of the C-star algebra. So it's easy to build such a map. The recipe for this map is you take a smooth compactly supported function on G0, you extend it to a smooth compactly supported function on G, and that's it. You study the class in the quotient C-star algebra. And by the universality of the max C-star algebra, that map extends to which was defined on CC infinity of G, extends to the max C-star algebra. It's not for free that you get some extension. You have to think about it, because remember, inside of this thing, if it wasn't for the 0, you could have some weird objects like this Kazhdan projection. So you've got to be careful. How are you going to define this map if there was a Kazhdan projection here? I mean, there isn't, because this particular group is amenable. But I'm just pointing pointing out that there's a little bit of room here. It's not obvious that this thing exists, but it does exist. Now, of course, this is the same thing as the reduced C-square algebra of G. And getting a map from C star of G into this algebra is all that's involved in improving this inequality here. When we studied how to prove continuity of continuous fields, for example, related to, I don't know, pseudo-differential operators related to the tangent groupoid, it was all about building such a map as this. Of this, yes. Oh, thank you. This is the main issue in obtaining this inequality. In fact, there was an exercise on this somewhere in the early months of the class, back when we were all young and energetic. So I'm sure you all did it back then, yeah.
So what you're saying here is that the direction is equal 0, like the sequence we can build, the reflection of 14 non-zero going to the G, going to the direction 0 is an exact sequence.
Correct.
You show that by building a splitting
That's correct, yeah.
for max algebra, and then
Yes.
the fact that
That's correct, yeah. When we were studying the Alain Connes' proof of the index theorem, there was a continuous field that needed to be proved to be continuous. And I mentioned that Connes did it using harmonic analysis, using some theory for the group R. And he was exactly using the fact that the group R is an amenable group. The same sort of trick was being applied by him. So we have a continuous field. And by what we discussed before in the realm of K-theory, we have a sheaf of abelian groups over R. Whose stalks are just the K-theory groups of the C-star algebras of GT. And it's a strange fact. So this is the so-called Kohn-Kasparov isomorphism, not conjectured by Kohn and Kasparov, proved later by a motley assortment of people. But this sheaf is constant. The sheaf whose stalks are these guys is isomorphic to constant sheaf. But roughly speaking, as you vary T, the K-theory groups don't change. This continuous field has the property that it has one special fiber at T is equal to 0. And all of the other fibers are exactly the same by virtue of this fact here. So in this situation, you can express this constantness in a different way. And this came up when, for example, we were discussing the index map. So in an earlier lecture, more than one earlier lecture, whenever you have a continuous field with this property that away from 0, it's a constant field. Whenever you have a continuous field over the real line, there's a map from the K-theory of the special fiber to the K-theory of the typical fiber, and that's just G. And to say that this field is constant is to say that these K-theory groups are all the same. So it's not, even by the standards of the index theorem, this is not at all an easy theorem. This is, I would say, much harder than the index theorem, but it's a true theorem. So for the types of groups, this is correct, by the way. You need to work just a little bit harder to make sense of what this theorem should say for any connected Lie group whatsoever. In fact, you can make sense of what this theorem says for any Lie group with a finite number of components. There's a version of this theorem, and the theorem is correct for all of them. And the main characters who worked on the reductive case are these two gentlemen, and the general case somehow is reduced to the reductive case by a bunch of others, Nest and Echterhoff, Chabert, et cetera, me and Kasparov, and so on. And the main question that we want to ask, not today, because there's only 5 minutes left, is the following. So here's a statement that's relatively speaking not a difficult statement to formulate. I mean, we've gotten kind of used to continuous fields of C-star algebras, and we've gotten kind of used to arguments like this. So it's relatively speaking not difficult to formulate this. And then you get a statement, a sort of universal isomorphism statement. Okay. The left-hand side here, a K-theory of the C-star algebra of G0. Remember, we had an explicit, it's disappeared from the board, but we had an explicit picture of what the K-theory of the C-star algebra of G0 is. It was functions on the space P star, some vector space with values in compact operators. That's not very complicated. If that was the end of what it was, then what we would be talking about here would just be the C0 functions from P star to compact operators, and the K-theory of that thing would just be the K-theory of P star. But we also have the K invariance condition to throw in. And what the K invariance condition tells you is that this thing here is, sorry for the preponderance of Ks, the K equivariant K-theory of the vector space P star. For example, in the sense, so Attir and Hirsebruch didn't really discuss equivariant K-theory, but Attir and Graham Siegel did. Let me just say the space. I just mean the topological space, which is P, or if you like, P star, they're isomorphic. And so it's basically something we understand. Very frequently, this P star is a vector space all the time. That doesn't happen frequently, it happens all the time. And we have the Bott periodicity theorem, which tells us what is the K-theory of a vector space. And very frequently, you can just calculate this thing, and what you find is just the representation ring of K. This thing is isomorphic to the abelian group, free abelian group on the irreducible representations of K. So this object here, it's the wrong sort of arrow. Don't mean a map, I just want to point to it. This is something, if you like, which is under control, and you can understand in easily understandable representation theoretic terms. So for instance, if G is SL2R, this thing is the representation ring of the K for SL2R, which is SO2. So we have a very concrete description of what this is. One of the things I haven't done in this class is define K1, or even discuss K1. 50% of the time, this vector space is an odd dimensional vector space, and then you really should be talking about K1 instead of K0. And I didn't do that. So in that 50% of the time, what you should do is take the group G and cross it with R. And now you're in the even dimensional case and you're back in business. So the question that you might now ask is, so in the Kohn-Kasparov isomorphism, there's one side of this thing which is completely understandable, even when it's not so completely under control that you can write down that it's the representation ring of K. It's certainly under control that you can calculate what it is. You can just write down an explicit set of generators all the time for what the left-hand side is. And so the question arises, what does this thing mean? This Kohn-Kasparov isomorphism mean? It's a simple statement. Two abelian groups are isomorphic. Unfortunately, you have to work really hard to prove it. After you've worked so hard, did you get anything of any value? Does it actually mean something? Well, that's an interesting question to debate. So we'll discuss this thing next week. We'll see if we can extract some. I'm not going to discuss how to prove this. I'm going to try and extract some meaning out of this statement, something which might interest a representation theorist. That's the goal. I think it's a good time to stop. Yes, on the nose, it's 12 o'clock. So we are done for today. Thank you very much. As usual, you've been a lovely audience. Thank the sponsors, yeah. Thank you to the Chips Ahoy Cookie Company for their... For nothing at all, damn it. They haven't given me a single cookie. All right, good. Thank you.
Things like, are we getting closer to like on things?
Yeah, this Kohn-Kasparov isomorphism is a special case of the Baum-Kohn isomorphism. And just in a couple of, I'm not going to talk about Baum-Kohn, but since you asked, let's consider the following thing. Suppose you have this is really it for Baum-Kohn. If you can resolve the following question, probably you should be happy. Just stop, not ask for anything more. Suppose you have a discrete subgroup. Maybe co-compact of one of these connective real reductive groups. If you like, all of the adjectives that I had before, I only wrote down a couple of them there. Then you can do the following thing. What's a good way of saying it? So you can think of gamma acting on G mod K. And what Baum and Kohn say is that the K-theory of the C-star algebra, this reduced C-star algebra of gamma, this C-star algebra is generally a terrible thing. I was talking before about the topology on the spectrum of a C-star algebra. I was saying before, you should think of the spectrum as being an interesting topological space. It's not in this case. Very typically, the topology on the spectrum of C-star reduced gamma is just the idiot topology with no open sets, except the ones required by law. Oops, now I built the map in the wrong way. Let's make my life a little bit easy. Let's just assume this group is torsion free. Here's the tangent space, or maybe to make it look more like what we had before. Like the cotangent space. And didn't mean C star, I meant the C0 functions. But what I actually want to do is take the functions in here, which you get after you've divided out by gamma. There we go. Right, number of parentheses and bits and pieces. That's a certain specific topological space. And there's actually a map from here to here. What is this map? Well, you just take the tangent groupoid for G mod K, and that tangent groupoid as a continuous field of C-star algebras is a bunch of compact operator algebras, except at 0, where you have the cotangent bundle, or the tangent bundle in the sense of groupoids of G mod K. And after Fourier transform, you have the cotangent bundle. On this tangent groupoid, the entire group gamma acts by diffeomorphisms, fiber-wise diffeomorphisms. And you can form the so-called cross-product C-star algebras. You can build gamma into the groupoid picture, if you like. And what the fiber C-star algebras are away from 0, excuse me, what the fiber C-star algebras are away from 0 are this thing. And what they are at 0, what it is at 0 is this thing here, at least it's Morita equivalent to this thing. So this particular map you get from this type of construction using the tangent groupoid continuous field after you've crossed, whatever that means, with gamma, form the cross, it's all still a groupoid, you form the cross product with the group gamma acting on the groupoid T of G mod K. So we're right there in a position to formulate the Baum-Kohn conjecture using the tangent groupoid. Maybe I'll put it in the notes or something.
Yeah, that's here on about the concept of like what the definition of normal have to do with it, other than just giving you what you don't want to do, like different.
Yeah, what does the DNC, what do this whole bunch of GTs have to do with this map? And because you can formulate this map in other ways, which don't use continuous fields at all, or deformations to the normal code. I think there's a compelling answer to that, which is this so-called Mackey bijection, which I'll talk about next time. There's something going on in representation theory which makes this more real. It makes you feel that this is the right way of thinking about the Kohn-Kasparov isomorphism. So I do plan to say more about that. I couldn't say it in 5 minutes, however. So in summary, I think there is a good answer to this what does it mean question, wherever it was. So here it is. I think the answer really involves the deformation space that we're building over there, the big G, in a serious way. And that those concrete meanings don't apply in the Baum-Kohn situation where the C-star algebras are more complicated. But okay, what this means so far is a different set of things related to implications in topology, but that's another story. All right, good.